Okay, we're going to get started now on first. Actually, I want to start chapter 5, but before I do this, there are a few loose ends that I need to talk about from chapter 4. Remember that we developed different methods for solving linear congruence equations. And I want to present one more method, actually using the Chinese remainder theorem. And this method actually applies, especially when the modulus is a composite number. So I'm just going to go through an example how this actually applies. And moreover, actually, as I mentioned, any polynomial congruence equation, you can actually use the method of the Chinese remainder theorem and solving linear congruence equation to solve higher degree polynomial congruence equation. We're not going to pursue that, but at least we want to do it for linear congruence equation when the modulus here is composite. All right, first of all, the greatest common divisor, we need to check if this has a solution. And yes, and 2 divides 30. This implies there are 2 incongruent solutions mod 30. All right, 2 distinct solutions. Now, we can reduce the coefficients of this equation by dividing by 2. So we get 11x is equal to 2 mod 50. The idea to use the Chinese remainder theorem is actually to consider a system that goes like this. This is congruent to 2 mod 5 and take 11x congruent to 2 mod 3. That's the prime factors of the composite number that we have. All right, then we're going to apply, apply the Chinese remainder theorem to solve this system of equations. Now, remember, actually, we even can reduce this system so that we can apply the Chinese remainder theorem by reducing the 11, all right, mod 5. So this gives us actually to just x, all right, because this is 11, I can actually take it 10, that's congruent to 5, so this equals 0. So this is this, mod 5. And the next one, we can replace the 11 by a number that is congruent to 3 mod 5, and that's 2. Okay, 2x is actually congruent, this is to 2 mod 3. All right, so 11 multiplied by this 22. Let me see in here. Actually, next one is congruent to, 2x. All right. So now actually subtract 9 out of this, which is congruent to 3 mod 5, we get this one. And also, since the 2, this 2 and the 3 are relatively prime, I can replace the second equation by x congruent. In other words, I can divide by 2 mod 3. And since it becomes 1, mod 3. And the first equation is x congruent to 2 mod 5. Now we apply the Chinese remainder theorem to this reduced system. Okay? And remember how we do this one? We create a linear equation that we can solve. Now remember doing this, it's actually reducing the modulus, okay? So this is actually is very helpful. So then we're going to find the M1 M1 is equal to 3. And we consider this equation 3x congruent to 1 mod 5. And the solution for this, just by inspection, all right, is 2. Okay, 3 times 2 is 6 minus 1 divided by 5. So this is 2. And then we consider M2. And this is equal 5. And we consider 5x congruent 1 mod 3. And the solution for this is 1 is not going to work. 2 give me 10 minus 1, yes. So x sub, let me call this is x sub 1, this is x sub 2, and this is equal to 2. All right, so we have these two solutions. Now we're going to combine these to give us one solution. All right, so which we call x is equal the A1, which is 2, multiplied by M1, which is a 3, multiplied by the solution. Then we have 1, the A in here, then multiplied by the M, which is 5, multiplied by the solution. So we combine these, we come up with 12 plus 10, that's equal 22. And we can reduce this, so this is mod, actually the product of these, which is 50. All right, now we could reduce this if we wanted to. This is congruent to 7 mod 15. So we have actually a solution which is 7. All right, and then the other solution, so x is actually congruent, or x equals 7 is a solution to the original congruence equation. All right. So the original congruence equation. Now the other solution is going to be 7 plus actually 15, which is 22. All right. And now this 22 again for the original equation. Okay, so mod 30. All right. So this is the other solution. All right. The other thing I want to talk about is systems of congruence equation in 2 variables, or 3 variables, or 4 variables. We don't want to go wide again. We're just going to illustrate the idea for 2 variables, and I will indicate how it is done for 3 and 4 variables. In fact, the method of solution is similar to what you have learned in high school, basically, or linear algebra, by doing the Gaussian elimination method. All right. Or we actually can think of solving these systems of linear equation as solving in the ring. If you are familiar with this, z sub something, okay, sub n. You know that we can do arithmetic in here, we can add and multiply mod n. And solving linear systems of equation is basically to do this elimination method, or the row echelon form, is by just applying, okay, what's called elementary row operations. And you can do this instead of using arithmetic in real numbers, you use arithmetic in this ring. Okay, so this is kind of the general idea. Again, I said we don't want to go very abstract here or wide. Let's just concentrate on systems of 2 linear congruences in 2 variables. And I want to state the theorem that actually, and you're going to see the similarity of this to just ordinary systems of linear equations. So this is theorem 4.9, and it states this: the system of congruences which is a x plus b y congruent to r mod n, and cx plus dy is congruent to s mod, the same modulus, okay? Where of course all these a, b, c, d, r, s, these are integers, and the n is a positive integer. So for this system, all right, has a unique solution provided that the greatest common divisor of AD minus BC and N is equal to 1. And of course, 1 of course divides the R and the S, usually what we have in here. Now notice that in this greatest common divisor, this quantity here, which is called the determinant for this system, or for the matrix, and you convert this into a matrix equation, so this becomes the determinant. And you would imagine that, you know, this must be, has some role in solving, because if I want to solve this, just think about it as, again, the A, the B, the C, and D are real numbers. We must, in order for it to have a solution, this must not equal to 0, okay? So it is reflected in here by requiring that the, you know, that the greatest common divisor equal 1, and this gives us all a unique solution. All right, the proof of this is basically doing elimination. Means just go ahead and solve this by eliminating the x or the y. We're going to actually do the elimination for both of the variables and come up with a solution. So here's the proof. Since I'm going to need the system in here, just going to leave this in here, and this is what I'm going to do, the proof. So I want to eliminate y, okay, from these two equations. So I want to multiply the first equation by d, and I want to multiply the second equation by negative b, okay? Now, remember, because I can think of this as like d is congruent to d mod n, and then I can multiply congruences. The same thing with the b. Negative b is congruent to negative b mod n, I can multiply those. So the result which we get is a new system, a dx plus b dy is congruent to rd, and we don't need to multiply the modulus by d. In here we get minus bcx minus b dy congruent to minus sb. Again, mod n. Now I can add two congruences, all right, and we're going to see that y is cancelled out, and then I can rearrange this and end up with AD minus BCX is congruent to RD minus SB. All right, mod n. So we end up with a single, so this is just a single linear congruence equation in one variable, in just the variable x. This is going to have a solution provided that the greatest common divisor of the modulus and the coefficient of x is equal to 1. Now, since we are given that, so this, since the greatest common divisor of AD minus BC and N is equal to 1, the equation has a unique solution. So the linear congruence equation has a unique solution. All right. So now let me look at actually this equation, which is sort of related to this. So we're going to consider the equation, which is AD minus BC. I want to take a different variable. Let me call it Z, is congruent to 1 mod N. And again, this actually does have a solution because the greatest common divisor. So in other words, I'm sort of getting a simpler equation. Instead of this, the right-hand side is being RD minus SP, I'm making it 1. Not making it, I'm producing an equation that has 1 in it. Okay, so this has a solution. Let's say T sub 0. All right? Now, I claim that x sub 0, which is equal T sub 0 multiplied by RD minus SP, is a solution to the equation in X, to the linear equation in X. It means that equation that we just have in here, this equation right there. All right? Let's check. Let's check. All we have to do is to substitute. All right? So we're going to substitute. So we have a AD minus BC multiplied by the x sub 0, which is T sub 0 on D minus SP. Okay, so we're going to check this is the actually left-hand side. And this is going to, of course, equal to AD minus BC multiplied by T sub 0 multiplied by RD minus SB. Or another way to, to do the same thing, basically, is when we substitute for T sub 0 for Z in here, we come up with this equation actually holds, and then you could basically, oh, that's not going to work. So I was saying multiply by the, RD minus SB. No, it's not. So this one, now, this quantity is actually congruent to 1 mod N. And this is, of course, we're just going to write it as is. So in other words, we see that the this value of x sub 0, so x sub 0 satisfies the equation, the linear equation in X. All right, so we find the value for X. Now, to solve the system, we need to find the value for Y. Now, what we could do, we could eliminate X in a similar way. Okay, so similarly, by eliminating X from the system, and we can accomplish this by multiplying the first equation by C and the second equation by negative A. And then just combine the two equations together, So by eliminating x, we obtain an equation in y. And by solving this in a similar way, this is the solution we obtain for y sub 0. So you're going to find out that y sub 0 is equal to t sub 0 as minus CR. The same t sub 0 that solved actually the equation for z. All right, now the claim is, which we want to make sure, so we find two values, but we don't know if these would satisfy the actually or the solution for the system. So the claim then is x sub 0, y sub 0 is a solution to the system of congruence. And to do this, we're going to do it like by brutal force, by just substituting. So we're going to substitute for x sub 0 and y sub 0 in each of the equations. In the system, of course. So let me check it for just one, and then I leave the other for you. So we have the, remember that we have ax plus by is congruent to r mod n. Alright, so now we substitute for x sub 0 by t sub 0. Then we have the x value is dr minus ps. Then plus the b and the y is t sub 0. Then we have as minus cr. And we would like to check if these numbers actually is going to be congruent to r mod n or not. If I multiply out this, I get a dr t sub 0 minus a b s t sub 0 plus a b s t sub 0 minus b c r t sub 0. Okay? Now we're going to find out that the middle terms in here, they cancel out. And we end up with, this is equal to, actually I can factor out an r between the first one and the last one. So we get, actually we can factor out also t sub 0. So we could do that. And then say this is ad minus bc rt sub 0. But the ad together with the t sub 0, with the ad minus bc t sub 0, remember this is actually congruent to 1. We have actually put them next to each other. So then I can say, so this is t sub 0 then times r. The first part here, this is congruent to 1, then r mod n. And this is it, it's satisfied. Similarly, you can check with the second equation and you see it will actually work. Now, to look at an example, really the proof is give us a method of solving. You remember that we're going to do this elimination for the x and then do an elimination with respect to y. All right, so here's an example. Actually, this one is given in the book. So let me just give the same example. So we have 7x plus 3y is congruent to 10 mod 16, and 2x plus 5y congruent to 9 mod 16. All right. Furthermore, notice that the greatest common divisor of AD, which is 35, minus BC, which is 6, and 16 is the same as the greatest common divisor, 29, 16. This is equal to 1, so we have a unique solution. Now, to do the unique solution, let's just start by eliminating the y. So if I multiply the first equation by 5, and the second by negative 3, we obtain here 35 plus 15 congruent to 50 mod 16. And the second equation becomes negative 6. So we need to put x and y in here, that helps, right? Okay. Then the second equation becomes negative 6x plus minus 15y is congruent to negative 27. All right, this is mod 60. All right, let's add up these. So we come up with, when we add, let me see here, 29, I suppose. All right, 29x is congruent to 50 minus it's 27, that is 23 mod 16. And we can actually even reduce the coefficients, mod 16, so this is equivalent to 29, give you 13, x congruent to 7, which is the 23 mod 16. And you can find a solution for this. I try another is x sub 0, it's going to be equal to 3. Similarly, when you eliminate y, you find that y sub 0 is equal to 7. And then this is the unique solution mod. So this is unique solution mod 60. Again, another way is, and this one you can generalize, is to actually consider, as I mentioned, the row echelon form, the method that you use in linear algebra. Okay, let me just point out how this is done. So in here we associate with this system what we call the augmented matrix. 10. And then we have 2, we have 4, 5, 9, and we reduce, okay, we do apply elementary row operation. In Z16. So you want to do arithmetic in Z16. Means if you want to make this is equal to 1, all right, you wanted to divide by basically 7 in some sense. And this means that you want to find a number when you multiply by 7, you come up with 1 mod 16, all right? What number you multiply by 7 to give you, 1. All right, we're going to be learning about inverses. Basically, we're going to find the inverse of this. That's what it is. And later on in chapter actually 7, mainly, and that's what we will be learning. And also, there is still some method that we're going to do in solving linear systems, just a single linear equation using actually inverses, which is very similar to solving algebraic equations like ax equal b. We know that if a does not equal to 0, then the solution of this is basically this. So we're going to see, something very similar to this method, but we need to find what we call the inverse of A mod the whatever the congruence equation is mod M. Okay. All right. So this actually concludes the chapter 4, and now I want to get started with chapter 5. All right. The title of chapter 5 is actually Fermat's. Sometimes we call it Fermat's little theorem or just Fermat's theorem. And its converse. So today I want to be talking about actually in this lecture only about Fermat's theorem itself and some of the some of its application basically, and I'm going to leave the converse, okay, for the theorem for a different lecture. All right, so the objectives here for this is very simple. For this chapter, first I want to basically give a motivation, all right, for Fermat's theorem, and then after that we're going to state and prove Fermat's theorem. In fact, we're going to give two different proofs. One which uses the concept of the complete residue system, nice and simple. And there is another proof, the original proof that was given by Euler. Okay, and I want to actually mention a little bit of history about Fermat's theorem. Then second, we're going to look at some examples. Okay. And basically, this is it. There's nothing much actually in this section or in this part, section 5.2. All right, other than just understanding, this here. All right. So let's get started in here with some motivation. All right, let's assume that we are, suppose we are given an integer, integer A, and a positive integer, integer N. All right, we're going to consider powers of A, like this. You're going to start with A, you have A squared, A to the third, A to the fourth, and so on. Now, we know that a complete residue system mod M has M elements that are incongruent mod M. In particular, the non-zero let me say the non-negative without the zero. How will we see how I'm going to say that? In particular, the least positive complete residue system mod M is this. Is 1, 2, 3 up to M minus 1. So to make this is a complete residue system, we need to add to this 0. Okay, so in other words, we need to add this is to 0 to make it a complete residue system. But I want to consider it without the 0. Okay. Now, another fact we know about this complete residue system, all right, is if you take any integer, then it's going to be congruent to one and only one of these numbers, all right, in this system, or could be 0, okay? So this is the case for any, okay, complete residue system. Now, when we take this powers of A, all right, and probably we don't want A to equal 0 here, and integer A does not equal to 0. So that's not an exciting kind of situation. All right, then we know that this sequence of powers is going to actually repeat, okay? So let me make this statement in here. Since so let me put actually the fact first of all. So we have a fact that for any integer x, let me make this is not multiple of m to avoid 0, not multiple of m, okay? X is going to be congruent to k, all right, mod m, for some k, for exactly 1k, or to say for exactly 1k in this range between 1 and m minus 1. Now, since we are taking all these powers, I don't know, none of these probably unless m a happens to be a multiple of m, okay, then the sequence of the powers of A, which is this one, A squared, and so on, or in this sequence of powers, then in, let me put the word in here to make the statement a little clearer. The statement of powers, let me exactly see the language I want to use in here, okay? Sequence of powers, we must actually eventually come to we will get repetition, some repetition. What does this mean? Okay, maybe the statement is it's not as clear as I'm making it, but let me state it in, you know, mathematical. That is, for integers or for positive, actually actually integers h and k. Let's say h is less than k. We have a to the h is gonna actually would be the same as, or a to the k, maybe the bigger one. A to the k is gonna be one of the other, the biggest powers of a. All right, mod. The reason for this, this sequence cannot be infinite, okay? Because each one of these numbers in it is going to be congruent to a k, all right? And the k is between 1 and m minus 1. So there are actually m minus 1 or m possibilities. We saved the, actually the 0, but for this at least m minus 1. All right, and this would imply that if since actually I wanted to add one more condition in here, that if we assume that the greatest common divisor of a and m is equal to 1, so these are relatively prime, then we can divide basically by the smaller of the exponents by a to the smaller exponent h, both sides by this, and this would imply a to the k minus h is going to be congruent to 1 mod f. All right, so this is what we get, and if I call this k minus h L, this integer by L, this implies that we have a to the L is equivalent to 1 mod m, where L is equal to minus h. All right. Now, so this is true for any A, any M, as far as these are, okay, actually congruent to each other. All right, in the case where M is a prime, and A is in Z such that the greatest common divisor of A and B is equal to 1, Fermat discovered that the smallest positive integer L such that A to the power L is congruent to 1 mod T is L equal B minus 1. So in other words, this is what Fermat basically discovered, that so to put it in one place, so Fermat discovery or discover for every A in Z E A prime such that greatest common divisor is equal to 1, A to the power P minus 1 is congruent to 1 mod B. And this is the smallest, okay? Because if this is true, of course, you can raise this to different powers. You know, any powers of P minus 1 is still going to give you 1. So this is the smallest one. And we're going to be talking a little more about this idea. In other words, P minus 1, we call this is actually the order, okay, of this integer A mod B. Now, Fermat communicated actually this discovery to his friend, his name, in a letter, okay? So the friend that he communicated this, his name is Bernard. I'm going to write just the name. I don't want to pronounce it because I don't know how to. Let's see. In a letter. And it's not exact dated. Okay, this letter dated October 18, 1640. And in the letter, he actually mentioned this discovery. And he states also in the letter that he would like to actually give a proof, but it would be too long for his friend. So he did not include actually the proof. And the proof wasn't actually discovered or found among Fermat's papers. The first proof of this theorem, which it became known as Fermat's little theorem, was given by Euler. And Euler not only actually proved Fermat's little theorem, which later on became like this, or Fermat's conjecture, if you wish, but he actually generalized it for modulus that is not actually just a prime, for composite moduli. We're going to be talking about the generalization of Fermat theorem, which we're going to call it from here on Fermat theorem, actually in chapter 7. All right? So for the time being, we're going to only concentrate on the special case where, we have a modulus that is a prime. All right, let me make actually a formal statement of Fermat little theorem, and then give a proof for it. Okay, so this is the theorem 5.1. And here it is. We're going to let B be a prime. And A, an integer in Z, such that AB is equal to 1. Now, let me mention a few other equivalencies to this, because it's worthwhile, having this. This is equivalent to saying that P does not divide A. Also, this is equivalent to saying that A is congruent to 0 mod P. Okay, any one of these statements, actually, these are equivalent to each other. This one is not congruent. So in other words, A basically is not equal to 0, all right, in this system mod P. All right? So if these conditions are satisfied, then A to the power P minus 1 is congruent to 1 mod. All right? So before we actually give the general proof for this, I want to look at a special case, and the proof actually follows pretty much the special case, okay? So let's look at an example to illustrate how, okay, we want to show 3 to the power 6 is congruent to 1 mod 7. It's not that we want to show this by following the method of the proof, for the general case. So in other words, we're going to do the proof as we're going to do it for the theorem itself. So we're going to start with, okay, we're going to start with a non-zero complete residue system mod 7 that consists of S, I'm going to put it 1, 2, 3, 4, 5, and 6. Then we're going to multiply S for each one of the elements in S. We're going to multiply S or the elements of S by 3. Elements of S by 3. So what we get what we call 3S, and this is going to be equal to 3, 6, 9, 4, 9, 12, sorry, 15, and 18. And then we're going to reduce this mod 7. All right, so let's put the results in form of a table. All right, and observe what will happen. Okay, so here it is. So we're going to make a table. And we have here the elements of S, which is 1, 2, 3. So this is S, basically. 4, 5, 6. And we're going to put in here the 3S. And we obtain the 3, 6, 9, 12, 15, and 18. Now we're going to do this is mod 7. So 3 is a 3. So in other words, this is a 3S mod 7. Okay, 6 will be still 6. 9 is 2. This one is 5. This one is 14, 1. And 18, take 14 is 4. So you notice that we obtain, okay, so this is the same elements in S, the original, in S, in a different order, in a different different order. Same number. Now, if I multiply the first row and the second row or the third row, we always get the same product. Okay? Well, the same product mod actually 7. Okay, so we're gonna multiply. So we're gonna consider the product of the first row or the product of the elements in the first row of the numbers in the first row and the product of numbers in the second row. So this is what we get. We get 1 times 2 times 3 times 4 times 5 times 6. Now we're going to consider this as again mod 7. Now remember, each one of these numbers, it turns out to be actually 1 times the 3. I'm just going to go back to the original, and then 2 times the 3, then 3 times the 3, then 4 times the 3, then 5, then 6 times the 3. Mod 7, of course, as we've seen in the third row, will be the same as these, all right? Now, in here we can rewrite this as 3 to the 6, right? Because we have 3 in each one of these factors, times, of course, 1 times 2 times 3, 4, 5, and 6, mod 7. So on the other side also we have this, we could write it as 6 factorial. And the right hand side we can write as also 6 factorial for this product. Mod 7. Now I know that 7 does not divide 7 factorial, 6 factorial, which is equivalent to saying that the greatest common divisor of 6 factorial and 7 is equal to 1. So I can divide this congruence relation by 6 factorial. So we're going to do that. So we divide by 6 factorial. Since it is relatively prime, then when I divide the modulus, it's going to be divided by 1. So we get 1 is congruent to 3 to the 6 mod 7. So yes, it turns out that the Fermat theorem actually does, or this verifies it for the A is equal to 3 and the modulus is the prime 7. All right, now we're going to move into prove the general Fermat theorem. And I want to start with actually stating and proving a technical lemma that basically take care of the whole, the main part of the proof, which is this complete residue system. We're going to say that when we multiply it by a number, it would give us the same thing. All right? So here's the lemma. I want to do it actually a little more general, not just for a prime. This is true for any integer. Okay, so we're going to let a be an integer, z, m positive, not necessarily a prime, such that a and m are relatively prime. Then the numbers which is a, 2a, 3a, up to m minus 1a are the same mod, this is mod m, are the same as these numbers. One, 2, 3, up to m minus 1, maybe in a different order. All right, this is what we actually have shown for the case with 7, right? All right, here's the proof. First of all, note that there are actually m minus 1 numbers in the, there are m minus 1 numbers in the first list, right? We just count them. This is 1, and so on. There's m minus 1. I claim that these numbers are actually, none of them are congruent to 0 mod f. Okay, so here's the first claim. K times A is not congruent to 0 mod m for every k between 1 and m minus 1. Okay? If we don't have any one of these, it's going to be congruent to 0. And then, of course, we're going to be congruent to those in here, right? When we just prove that they are distinct, that's what. All right. So let's assume, well, no, we have this is congruent to 0. So this is, can prove this claim by contradiction. So let's assume that K A is congruent to 0 mod f. For some K, between 1 and m minus 1. Well, now since we have since A and M are relatively prime, then we can divide by A, and this would imply that K is congruent to 0 mod M for that K between 1 and m minus 1, and this implies that m divides K, but this is a contradiction because actually K is less than, since we have K is less than or equal to m minus 1. So it cannot be a multiple of m. Alright, so we have none of these is actually again congruent to 0 mod. Alright, we have another claim that the numbers in the first list are incongruent pairwise. They are not congruent. None of them is congruent to another one. Okay, so here's another claim. Okay, claim number 2. The numbers in the first list are incongruent mod m, of course, pairwise. What does this mean again? That is J A is not congruent to K A for every J does not equal to K less than or equal M minus 1. So all integers between, as far as they are not equal to each other. Again, I'm going to prove this is by contradiction. So let's assume they are. And J A is congruent to K A for some. J does not equal to K. And these are mod, of course, here, mod M. So we need to put mod. Well, what does this imply? This implies that M is going to be divisible by M divides. And we could factor out that A, J minus K. All right. Just for simplicity in here, let's assume that actually the K is smaller than J. Okay, so since they are not equal, so one must be smaller than the other. So let me take that J is actually smaller. All right, now we have, since M does not divide A, right, they are relatively prime, this implies M must divide J minus K. All right, but now this what we have in here. We have 1 less than or equal J, K is the smaller one. Less than J, less than or equal M minus 1. So when I subtract, so this implies that actually J minus K is going to be smaller than or equal M minus 1 as well. All right? And now M divides J minus K, and J minus K is less than or equal M minus 1 occur only if the J minus K is equal to 0. The only way that M is going to actually satisfy this at the same time smaller, that it must be equal to 0. Because I don't know what it is. I cannot say we have a contradiction, okay? Because it is possible that this is equal to 0. That's what it happens. And this implies that J must equal K. All right? So in other words, yes, the claim is true. Now, one other thing we need, remember we're going to show that the two lists are actually equal to each other mod m, right? Or so from what we have shown now, so since the numbers in the list, which is 1a, 2a, and so on, up to m minus 1a, are distinct mod m and there are m minus 1 elements, then each one of these must be congruent. Then each one must be congruent to, of course, congruent mod m, to exactly one of the numbers in the list, in the second list, basically, in the list 1, 2, up to m minus 1. All right, of course, in some order. And that's all we have. One more time, remember that we are using the fact that any number is going to be congruent to one and only one from this complete, okay, actually residue system. And only one is missing from here is the 0, but we have shown that none of these is congruent to 0 mod m. So it must be each one of the, and none of them are congruent to each other. They are not congruent in pairs, so they are different, animals for mod m, and which make this thing the same. So really, what we are, another way of saying what we have shown that this is actually together with 0. If I add it to this 0, then I get a complete residue system. Okay, mod m. All right, now we proceed to the proof of Fermat theorem, which is going to be just basically very simple. Okay, all I have to do, since the two lists which is, let me put with a to a up to m minus 1a, and 1, 2 up to m minus 1 are the same. Mod m, then their product are the same Actually, let me be more careful here. Let me actually consider the less when m is a prime. I want to take this one out. Okay? Because actually it's not true for any. It's going to be different, basically. All right? Now, in here, let me actually start with this. Let p be a prime. And a, b is equal to 1. Then what, by the lemma we have this. All right, be a little more careful in here that a to a up to b minus 1 a mod m, mod b, sorry. And this list 1, 2, up to b minus 1. We don't need mod in here because it's not going to change anything. Are the same. Now we're going to take their product. So this implies that if you take A, multiply by 2A, 3A, up to B minus 1A, this is going to be the same as mod M, 1, 2, up to B minus 1, mod B. Once again, if we take the A out of all of these, we get a to b minus 1 multiplied by 1, 2, and so on, up to b minus 1. And this is congruent to this part. Mod b. So in here we can write this as a to the power b minus 1 multiplied by b minus 1 factorial. And on the other side, we have b minus 1 factorial. Mod b. Now, since b does not divide b minus 1 factorial, remember that b minus 1 factorial doesn't have one of its factors, b. It starts from b minus 1. So this, again, we can divide. By b minus 1 factorial, and we obtain a to the power b minus 1 is congruent to 1 mod. All right. Before we look at some examples, let me look at actually a corollary to this. Now remember we put some restriction on A to be relatively prime to P. Turns out actually if A is not relatively prime to B, then we have another statement. So this is a corollary. And sometimes actually Fermat's last theorem is stated this way. Okay? So it could be stated in terms of a to the power b minus 1 congruent to 1, or this. So let p be a prime. And a is any actually integer, then we have a to the power b is congruent to a mod p. So we have this. And the proof goes like this. You know that any A in Z, either the greatest common divisor of this equal 1 or is equal B. All right? Either 1 or bigger than 1, in that case it's going to be actually B. If AP is equal to 1, then by Fermat theorem, we have A to the power P minus 1 is congruent to 1 mod P. Then we can multiply this by A. It would imply that A to the power P, because A is congruent to A mod P, and then we use that property, and this is mod P. Otherwise, if A, P is equal P, this implies that P divides A, and this is equivalent to saying that A is congruent to 0 mod P. Also, you can raise this congruence to P. So this is A to the P is congruent to 0 to the P mod P. And this means that the A to the P is congruent to 0, but A is also congruent to 0 mod P. And we are done. So this one is just implies that we have A to the P is congruent to A mod P. Both of them congruent to 0 mod P. That's all. All right. Now let's look at some examples, some of the calculations that we can, or Fermat actually theorem can simplify. All right, here is a couple of examples I want to look at. Actually, let's see in here. Yeah. Examples. Start with the first one. I want to find, show that 3 to the power 201 is congruent to 3 mod 11. Another way to state this is the remainder of dividing the 3 to the power 201 by 11 is equal to 3. So there's a lot of ways we could actually do this. Now to show this, what we're going to start with is by Fermat theorem. We have the 3 to the power of 10, which is 11 minus 1, is congruent to 1 mod 11. Of course, this means 3 to the 10 is congruent to 1 mod 11. Let's raise this to the 20th power. Okay, so we can raise this. Remember that this property actually holds with raising to the 20th. Still, this is mod 11. Now the left-hand side becomes a 3 to the power 200 is congruent. The right-hand side is 1 mod 11. And then if I multiply both of this by 3, we get the required congruence mod 11. Remember we did some similar calculation to this using this successive squaring. But now we can do this one in a much easier way. Another example is find the, this time we're going to say it in the form of a remainder, okay? The remainder of dividing 5 to the 100th power, okay? Example 2, we're going to find the remainder of dividing 5 to the 100th power by 7. Of course, forget it to try to do this one, you know, by brutal force. Means calculating actually 5 to the power 100 and try to divide by 5. All right, again, we're going to apply by Fermat theorem. We're going to start by looking at 5 to the exponent 6. So this is congruent to 1 mod 7. And we can raise this to a power to get as close to the 100. So here it is. Well, if you raise this to the power 16, this is going to give you 1 to the 16, and again mod 7. Now, 5 to the 6 to the 16, this gives you 5 to the 96. So this is congruent to 1 mod 7. Again, we could multiply this by 5 to the 4th. So we get here what we want, and we get here 5 to the 24, x to the 4. And even this one I can write as 5 squared times 5 squared, and I can reduce each one of these mod 7. So 25 mod 7 is going to be equal actually to, let's see here, this is 25, subtract from this 14, I suppose, or 21. 21, so we left with 4. And again, this is 4. And now this is 16, which you can see this is congruent to 2 mod 7. So the remainder is going to be actually, the remainder here is going to be equal just to 2. All right. We give one final example, slightly different, but along the same lines. So I want to find the remainder dividing a sum of 2 numbers by another number. In this case, or we put it a different way. We're going to show that, so it means the remainder is 0. 2 to the 50 plus 3 to the 50 is divisible by 30. Again, we're going to apply Fermat theorem to both this one and this one, mod 13. So we start with 2 to the 12, which is 13 minus 1, is congruent to 1 mod 13. Yeah, we want to build this to get it up to 50. So we're going to raise this to the power of 4. So this is going to be also 1 to the 4th, which is 1 mod 13. So this gives me 2 to the 48. I'm going to 1 mod 13. And then I can multiply by 2 squared, right? Multiply by 2 squared, and we get 2 to the 50 is congruent to 4. Sorry, 4 mod 13. Similarly, I can do the 3 to the power of 12. is congruent to 1 mod 13. This time I want to raise this is to the power of, let's see, 12, again 4. Okay, so go to the 4 here. So this 48 is congruent to 1. And now we multiply by 3 squared. So we get the 3 to the 50 is congruent to 9 mod 13. Now we can add this congruent to this congruent. Then we get 2 to the 50 plus 3 to the 50 is congruent to 4 plus 9, which is congruent to 0 mod 13. All right. So Fermat's theorem, basically it makes the, raising powers or taking powers, mod, congruence powers is actually very simple. All right. I was gonna give another proof for Fermat's theorem. I guess I'm gonna postpone this till next time. Okay. We're gonna look at another proof at the converse of Fermat's theorem, which is actually a very interesting situation. All right, we're going to find the converse is not true, and it turns out that because it's not true, all kind of ideas, okay, developed to use it for actually what is called the primality testing, okay? So I'll be talking about this a little more in the future. All right, actually the next lecture is it. All right, gonna stop right here.